In the first lecture on curvilinear coordinate system, we have seen some of the important terms of definition. That is, what are coordinate curves, coordinate axes, coordinate surfaces. All these things have been defined in the first lecture on curvilinear coordinate system. Actually, to discuss the theory of curvilinear coordinate system, we need the concept of unit vectors. So in this lecture, we will see the two sets of unit vectors which are needed to discuss the concept of curvilinear coordinate system. For this, let us see this figure. In this figure, you can see, this figure is just which we have drawn in the first lecture. Here in this figure, you can see there are actually three curves. First curve is known as U1 curve, second one is U2 curve, and the third is U3 curve. Actually, how these curves are obtained? In fact, I have not shown in this figure, but in the previous lecture you have seen there are three surfaces defined by the equations U1 equal to C1, where C1 is a constant, U2 equal to C2, where C2 is also another constant, and U3 equal to C3. Actually, these three coordinate surfaces intersect one another along a curve, and these U1 curve, U2 curve and U3 curve are actually the intersection of the two coordinate surfaces, and all these curves meet together at a point P, whose position vector in this figure has been shown by the vector r with respect to a Cartesian with respect to the origin of a Cartesian coordinate system. Now, actually, in curvilinear coordinate system in general, there exist two sets of unit vectors. You can see in this figure, the first set of unit vector is denoted by the symbol a small e1 hat, a small e2 hat, and a small e3 hat. And the another set of coordinates, another set of unit vectors are denoted by the symbols capital E1 hat, capital E2 hat, and capital E3 hat, as you can see in this figure. In fact, these unit vectors, a small E1 hat, E2 hat, and E3 hat, are the unit vectors along the tangent to the coordinate curves. You can see this unit vector E1 is tangential to the point P on the curve U1, and similarly the unit vector small e2 you can see here is actually tangential to the curve U2, and similarly the unit vector E3 is tangential to the curve U3. So this set of unit vectors E1, E2, E3 denoted by the small letter are actually the tangential unit vectors, you can say. But there is another convention too to select a set of three unit vectors, and that convention is what? We draw a unit vectors normal to the coordinate surfaces. So you can see here this E1. This E1 is normal to the coordinate surface defined by this equation. So this E1 hat, capital E1 hat, this is normal to this surface U1 equal to C1. And similarly, the unit vector capital E2 hat, this is normal to the coordinate surface defined by the equation U2 equal to C2. And the third one, that is E3 hat, this is normal to the coordinate surface defined by the equation U3 equal to C3. So these are the two sets of unit vectors which will be used in the discussion of the theory based on curvilinear coordinate system. In fact, these two sets of unit vectors become identical when you consider that the coordinate system is orthogonal, and in practice almost everywhere we consider the orthogonal coordinate system. So if you will consider that your coordinate system is orthogonal, it means the coordinate surfaces intersect one another at every point perpendicular to one another, then there is no difference between these two sets of unit vectors. It means in that condition, this E1 hat and this capital E1 hat are not different, but they will be same. And similarly, E2 hat will be same as that of the capital E2 hat, and E3 hat will be also same to the capital E3 hat. Now, for your convenience, you can see I have written all these things which I have just interpreted in this lecture. So you can see I have mentioned all those facts here for your convenience. You can note these things in your notebook and for your examination purpose. And now we want to express these unit vectors in terms of a very useful quantity which is known as a scale factor. And for this, let us see this figure first of all. You can see, as I have told you earlier, that this point of intersection P is at a distance r from the origin of this Cartesian coordinate system. So you can say that in Cartesian coordinate system, the position vector of this point P with respect to O is r. As you have seen in the previous lecture that some transformation equation exists. So this position vector r can be expressed as a function of the generalized coordinates u1, u2 and u3. You can express it. And all these things you have seen in the earlier lecture. And if you want to express this position vector r in Cartesian coordinates in terms of its rectangular components, then you know r is expressed as x1i plus x2j plus x3k. Actually, here for convenience, I have used the symbol x1 for the x coordinate x, and the symbol x2 has been used for y, and the symbol x3 has been used for z for convenience. And as that you have seen the transformation equation in the previous lecture, that we can express r as a function of the generalized coordinates u1, u2 and u3. In fact, in this condition you have also seen that the vector del r by del u1, this is actually along the tangent to the curve u1 at point P, but only when the other coordinates u2 and u3 are constants. So you can say that this del r by del u1 is along the tangent to the curve u1. So if you want to define a unit vector along this tangential direction, you can easily define, because you know a unit vector is defined by in a particular direction is defined by a vector in that direction divided by modulus of that vector. If you want to define a unit vector, let us say a hat, which is in the direction of this capital A vector, then a hat is simply defined by a vector A divided by mod of vector A. Similarly, if you want to define the unit vector along this vector del r by del u1, which is actually along the tangent to the curve u1, then you can easily define by this idea of unit vector. So you can say the unit vector tangential to the curve u1 at P is given as E1 hat equal to, this will be del R by del U1 and divided by mod of del R by del U1, and you can write it del R del U1 and divided by H1, where we have assumed that this H1 is simply equal to mod of this del R by del U1. So in this way we define the tangential unit vector E1 hat, and so from this result you can define the vector along the tangent del R by del U1 will be what? This will be simply H1 E1 hat. You can see when you will find del R by del U1, this will be H1 E1 hat. And in this way you can also define the other two tangential unit vectors E2 hat and E3 hat, observing this result which we have just obtained. So you can say similarly if E2 hat and E3 hat are the unit vectors tangential to the U2 curve and U3 curve, then in the light of this result you can write what will be del R by del U2. Del R by del U2, instead of H1 here we will write H2, and instead of E1 we will write E2, where you can say that this H2 is equal to what? This will be mod of del R by del U2, and similarly del R by del U3 will be equal to H3 E3 hat, where you can say this H3 is equal to mod of del R by del U3. Actually these quantities H1, H2, H3 which we have just defined are known as scale factors, and you will see the utility of these scale factors in the forthcoming lecture in developing the theory of generalized curvilinear coordinates. So these H1, H2, H3, what are these? These are known as scale factors. So remember the results. Now as I have told you earlier that there are two conventions to select the set of unit vectors in discussion of generalized curvilinear coordinate system. And we have discussed here the one set, and in the first set you have seen these small e1 hat, e2 hat and e3 hat are actually the tangential unit vectors. Now in another convention we use the another set of unit vectors denoted by the symbol capital E hat, and these unit vectors are defined in another manner. As you know, if there is a surface, let us see, this surface is u1 equal to c1, where c1 is a constant. Then you have seen in the vector calculus that the gradient of u1, that is del u1, is normal to this surface. If you will draw here a tangent, and you know this tangent is along the direction of e1 hat, then according to the geometrical meaning of gradient of a scalar function, you have seen that gradient of this u1 will be normal to this surface. This is just the geometrical meaning of gradient of a scalar function. So if you consider that there is a point P on this curve u1, this surface u1 equal to c1, and this is actually known as a level surface, then gradient of u1 is normal to this level surface, and this is nothing, this is simply the geometrical meaning of gradient of a scalar function. So we know as del u1 is a vector normal to the surface u1 equal to c1. So if you want to define a unit vector in the direction of this vector del u1, what you will do? It is very easy. You can say, when you will divide this vector del u1 by modulus of this vector, then you will get a unit vector in the direction of this vector del u1. So you can define it. Therefore, a unit vector e1 hat, capital E1 hat, normal to the surface u1 equal to c1 is defined as, how you will define? E1 hat will be defined as the vector del u1 divided by modulus of del u1. Modulus of del u1. And in the similar manner, you can say the unit vectors normal to the other two surfaces, that is u2 equal to c2 and u3 equal to c3, can be defined in similar manner. So similarly, unit vector normal to the surfaces u2 equal to c2 and u3 equal to c3 are, what will be these unit vectors? Capital E2 hat, this will be del u2 over mod of del u2, and normal to the surface u3 equal to c3, the unit vector will be e3 hat equal to del u3 over mod of del u3. So in this way we define the two sets of unit vectors in generalized curvilinear coordinate system. Actually these two sets of unit vectors, as I have told you earlier, will be just identical if our coordinate system is orthogonal. Now you can see some of the important facts regarding this concept. First of all, we have two sets of vectors. First set are tangential vectors and another are normal vectors. You can say the tangential vectors are del r by del u1, del r by del u2 and del r by del u3. You have seen these vectors are called tangential vectors because these vectors are tangential to the curve u1, u2 and u3. And similarly, the normal vectors. Normal vector means vectors along the normal direction of the coordinate surfaces. So normal vectors are del u1, del u2 and del u3. You have seen that these vectors are normal to the coordinate surfaces u1 equal to c1, u2 equal to c2 and u3 equal to c3. Actually, these two sets of vectors constitute a reciprocal system of vectors. And when you say that these two sets of vectors constitute a reciprocal system of vectors, what does it mean? It means whenever you will take the scalar product of the tangential vector del r by del u1 with the normal vector del u1, then your result will be equal to 1. And similarly, the product of this del r by del u2 and del u2, this will be 1. And in this way, the scalar product of del r by del u3 and del u3, this will be actually equal to 1. But when you will take the scalar product of two dissimilar tangential and normal unit vectors, the result will be simply 0. So we say that these two sets of vectors form a reciprocal system. So these form a reciprocal system. And when you say that these two sets of vectors form a reciprocal system, what does it mean? It means del r by del u1 dot del u1. This will be equal to del r by del u2 dot del u2, and this is equal to del r by del u3 dot del u3, and all these will be equal to 1. Actually, this is a most important result, and these results will be used very frequently when you will solve the numerical problems based on this concept. And at the same time, the scalar product will be 0 when you will take the a scalar product of tangential and normal vectors of different nature. You can see here that del r by del u1 dot del u2 and del r by del u2 dot del u1. This will be equal to 0. And similarly, you can say del r by del u2 dot del u3. This will be equal to del r by del u3 dot del u2, and this will be also 0. And similarly, you can say del r by del u1 dot del u3, and this will be equal to del r by del u3 dot del u1. These are also 0. So these two sets of result actually shows that the set of vectors del r by del u1, del r by del u2, del r by del u3 and del u1, del u2, del u3 constitute a reciprocal system of vectors. Now, as you know, if there be any vector in a space, that vector can be expressed in terms of their components. Since in generalized curvilinear coordinate system you have seen there are two sets of unit vectors, so any vector in generalized curvilinear coordinate system can be expressed in two ways. That is either in terms of the tangential unit vectors or in terms of the normal unit vectors. So let us consider in general there is a vector f. Consider a vector f. Now if you consider that f1, f2, f3 are the components of f in the direction of E1 hat, E2 hat and E3 hat, then you know this vector f can be expressed as f1 E1 hat plus f2 E2 hat plus f3 E3 hat. We can express like this. And similarly, if you consider that the small f1, f2 and f3 be the components of vector f along the normal unit vectors, that is capital E1 hat, E2 hat and E3 hat, then the given vector f can be also expressed in terms of these unit vectors. That is, this will be written as f1 E1 hat plus f2 E2 hat plus F3 E3 hat. So here you can say that this capital F1, F2, F3 and a small f1, f2, f3, these are actually the components of vector f in the two systems. Now the vectors del r by del u1, del r by del u2 and del r by del u3, or del u, del u1 or del u2 or and del u3, these are not unit vectors, but these are the vectors from which we can find the unit vectors. So actually those vectors are known as unitary base vectors. So you can say del r by del u1, del r by del u2 and del r by del u3, and del u1, del u2 and del u3. Actually these two sets of vectors are known as unitary base vectors. Unitary base vectors. Although these are not unit vectors, when you will divide these vectors by modulus of the same vector, then you get the unit vector. So these are not unit vectors, but these are the basis from which we can find the unit vector. So these vectors are known as unitary base vectors. Actually, any vector in a space can be also expressed in terms of these unitary base vectors instead of the unit vectors. Particularly when you will study the linear vector space in quantum mechanics, then you see that in quantum mechanics there is a tradition to express a vector in terms of unitary base vectors, not in terms of unit vectors. So this idea is most useful when we discuss the linear vector space, particularly in quantum mechanics. So as I have told you, instead of the unit vectors a small e and a small or capital E hat, we can also express a vector in a space in terms of these unitary base vectors. So in terms of these unitary base vectors, f can be written as vector f. You can write it c1 del r by del u1 plus c2 del r by del u2 plus c3 del r by del u3. And similarly, you can also express this vector f in terms of the unitary base vector del u1, del u2 and del u3. But components will be different. Here c1, c2, c3 are actually the components of vector f in this case, and when we will use the another set of unitary base vector, components of vector f will be changed. And let us consider these components are alpha 1, alpha 2 and alpha 3 in this set of unitary base vectors. So in this condition you can express this f in this way. This is alpha 1 del u1 plus alpha 2 del u2 plus alpha 3 del u3. So you can see this is also a convention or tradition to express a vector in terms of the unitary base vectors instead of the unit vectors. Actually, this idea, as I have told you, is very useful while discussing the concept of linear vector space in quantum mechanics. And also, this idea is very useful in tensor analysis. When you will study tensor analysis, you will see these components C1, C2 and C3 are known as actually the contravariant components of this vector F. So a vector has contravariant components when we express the vector in terms of the unitary base vectors, which are actually along the tangent. But these alpha 1, alpha 2 and alpha 3 are known as covariant component of this vector F. And this contravariant and covariant components of a vector is a very useful concept in the tensor analysis. So you can say here, what are these C1, C2 and C3? These C1, C2 and C3, as I have told you just now, that these are called contravariant components of F. These are called contravariant components of F, and the components alpha 1, alpha 2, alpha 3, these are called covariant components. Covariant components of F. So this is the idea of unit vector and unitary base vector in generalized curvilinear coordinate system. But you will find the use of this concept in the forthcoming lecture. So for simplicity, I am ending my lecture at this juncture, and in fact we will use the idea which we have developed in this lecture vividly in the forthcoming lecture.